Okay, there we go.
Right, it's good.
Perfect. Thank you.
All right, so let's get started here. And I have a really interesting and exciting topic that I want to talk to you about. So let's get going as to what the problem is. So as you know that storage systems are obviously not only very important for clouds, there's also a lot of development in the storage technologies lately, and there's a lot of excitement and activity in this area. And obviously, all of that excitement is warranted because our data needs are increasing. Continuously, we need more and more data, and not just storing the data, but we want to access that data as efficiently as possible. So if you look at some of the technologies, for example, so for a very long time, we had the hard disks and the access time of something like 5 milliseconds. And for last maybe 10 years or so, we have been using SSDs, solid state drives of increasing capacity, and they will give you a access latency of the order of hundreds of microseconds. But they have been continuously increasing in performance, meaning lower latency and higher bandwidth. And now there are new technologies. For example, Intel has this technology called Optane with about 10 to 20 microsecond access latency and bandwidth as good as SSD or even better. And then you have the persistent memory technologies, which begin to compete with DRAM. They have less than 1 microsecond latency. So in all of this, it would be nice to be able to provide quality of service treatment to the application depending upon the needs of the application. And that's the part that's not quite so easy, and that's what I want to talk about today. All right, so I guess the first thing to note here is that, as you are all familiar with this, that SSDs hide a lot of stuff inside. They are not at all like hard disks. They have a lot of issues that they need to tackle, including particularly garbage collection that they need to do. And as a result, what happens is that there's a lot of background activities that every once in a while the SSD has to carry out. So if you look at the tail latency can easily go into milliseconds, as you can see in the graph here to the left. So on the x-axis, you see this 99.9 percentile latency, 99.99 percentile latency. And you can see that the latency really shoots up occasionally, particularly when it's doing garbage collection. There are other emerging technologies that do not have this problem, but they're expensive. And there are two technologies, particularly the phase change memory, commercialized by Intel as Optane, and then the magnetoresistive memory, such as STT-MRAM. Those are the two fairly mature technologies. There are a whole bunch of other technologies. So here is a brief chart which tells you about what's going on in terms of the shipments of these technologies. As you can see that NAND, of course, is the dominant, and it's very high volume. And then the 3D Xpoint, which is Intel's Optane technology, it's ramping up pretty nicely. And then you have the MRAM, which is fairly small at this point, but hopefully it will grow. Okay, so a few tidbits about the cross-point technology. Well, it comes in both storage and memory format. And the key difference between storage and memory is these are two completely different usage models. A storage model typically means that when you make a storage request, you basically, the thread that's making the request gets switched out, and then you get the response back, for example, for a read, and then the thread gets back switched in. Whereas with the memory, the typical way of operating is that the CPU just waits for the response from the memory. And if that is the case and the memory latency is high, then the CPU is going to essentially get killed. It will not provide you any performance. So a low latency for memory is a lot more crucial than a low latency for storage. Okay, so what is the problem? So I already talked about the SSD issues, and hopefully some of those issues can be addressed, and I will show you using some of these emerging technologies. But we have another issue here, which is the network. So for the longest time, we never thought that the storage could saturate the network, because a hard disk obviously cannot. But a SSD can. In fact, the SSDs have become so fast that if you put in a couple of SSDs on a 100 gigabit network, they can really eat up all of the bandwidth. So here are some numbers that you can see, for example. So at the bottom, for example, you see that a single SSD, this is not multiple SSD, this is single SSD with a sequential read, it can put out 28 gigabits per second, which means that you couldn't possibly handle 3 of these at their peak rate on a 100 gigabit network. Even a more reasonable one where the queue depth is 8, that means 8 requests are pending, you have about 14 gigabits per second. So the network, which for the longest time we thought is fast enough for storage because the storage used to be very slow, is no longer the case. However, obviously you're not driving the storage at its full capacity all the time. Particularly, what happens is that you see these spikes in storage accesses. So there are these essentially congestion episodes or high access rate episodes, but a lot of the time the storage access is not that much. So that sort of gives us hope that means that you don't necessarily have to put gobs and gobs of network bandwidth. You can manage the network bandwidth if you basically know how to manage it using the proper QoS treatment of different classes. So this has a lot of very interesting applications or interesting implications rather, and we have done a lot of work on this, and I'll talk about some of these. Okay, so coming back to the tail latencies that I was talking about. So as you can see here, this is a diagram provided by Intel, for example, and it talks about Intel technologies. So on the top, you see what happens to the SSD as a function of the total bandwidth that you drive. The latency increases very rapidly. In the middle, you have the Optane SSD, which is the Optane technology, but in the storage mode. And you can see that it's very flat. Okay? Of course, at the end, it spikes up, but it's very flat. And then you have the Optane memory, which is, again, very flat for the longest time. And then, obviously, at the end, it spikes up. So what we would like to see is we'd like to see a behavior of these two technologies that are here as opposed to the SSD behavior. And the reason is that there are increasingly stringent storage requirements, and the companies are clamoring for what they call as deterministic latency. Obviously, the term is not technically quite correct because it can't have exactly deterministic latency, but what deterministic really means in practical terms is that they have a very short tail. That is, you don't want this occasional scenarios where the SSD, for example, it's doing its thing and the user doesn't get a response for a long time. So you want a much more shorter tails, much more deterministic latency. And here is another chart again from Intel, and it shows you what happens to the tail of the latency. And it's a little bit hard to read, but these are different levels of tail. For example, here is 99.99% latency. And you can see that these latencies are also kind of flat over the IOPS range. Okay, so, which is a good thing. Okay, so obviously the reason I'm talking about both the SSDs and the other emerging technologies is we're going to use those technologies together in some ways to get better performance. All right, so now what is the problem of QoS in a storage system? Why is it so hard to provide QoS? Because after all, QoS is probably the oldest topic in computer science, and people have been talking about this forever. The problem is that that most of the storage that is used is a block storage as opposed to the object-based storage, meaning that the storage device sees the storage as just a bunch of blocks. And it doesn't really have any notion of which application is accessing which block or what QoS needs it has and so on. It's just a bunch of blocks, and it can do a fantastic job in terms of serving those blocks as fast as it can. It can also, if you somehow designate, let's say, the different classes of blocks for somehow, it can also provide the QoS to them, but it doesn't have any kind of a connection to the application. And that's a huge semantic gap in storage systems. So on one side, we have the applications, and the applications think possibly in terms of files, and they don't know all the complexity of the storage systems. Storage systems are horrendously complex. There are multiple levels of virtualization. And what is missing is this sort of a connection between the two. Okay, so if you go from host to all the way to the target, target meaning the device, you have the QoS issues to handle in the host. You have the QoS issues to handle in the network. You have the QoS issues to handle on the storage server and the protocol side, and then in the device itself. Now, I neglected to say this, but nearly all of the storage access in a cloud or in a data center is over the network. And that is for reasons of being able to manage this efficiently. You want to centralize the storage and then be able to manage it properly and provide any amount of storage to any application that needs it, as opposed to fragmenting it all over the place. So network is an integral part of storage access, and that leads to further problems, particularly when we are talking about this issue of the storage being able to saturate the network. So what we got to do really here is to provide the QoS. We need an end-to-end hinting from application, or at least the operating system, all of the way to the devices, so that every layer in between knows about what the QoS requirements are and accordingly provide the treatment. And there are a lot of challenges in doing that. So first of all, there is a question of how do you define the policies? And obviously the policies need to be tail latency centric. We're no longer talking about average latency because it's the tails that matter. And then obviously, if you're going to specify the tail latency, you need to specify the the tail latency contribution for every portion and how it all composes together so that you get the overall tail latency that's acceptable to the application. And then there's a whole question of how do you define these hints and how do you convey them end to end? And that actually, that provision is not there actually in the different storage protocols. You need to make some changes to the storage protocols, which is always very, very painful thing. Although some of it exists, but it's not universally accepted. And then there is a question of once each layer gets the hint, then how does it translate that QoS requirement into whatever mechanisms that it locally can provide? And that's not an easy thing to do. And then finally, and by the way, it's absolutely important that all of the treatment that these different layers provide, that be harmonious. So for example, if one layer provides a good treatment and the other layer provides not so good treatment, you're not going to get the desired end-to-end QoS. And finally, there's a question of admission control when you cannot provide the QoS. Okay, so that's sort of the entire landscape of QoS, and there are a lot of issues in there. And then there are, of course, emerging technologies that I will talk at the very end a little bit to give you an idea that, well, even if you can solve the existing problem, there are more problems coming up. Okay, so I've been talking about end-to-end, and what exactly is end-to-end? Well, traditionally, we think about end-to-end from a single host to a single storage server or even a storage device. But obviously, in reality, the situation is a lot more complicated. You could have a single application which is using storage from multiple storage servers. And obviously, all of it is going over the network. And all of these need to be sort of coordinated together, because if one storage server is giving a good service, the other one is not giving such a good service, then obviously the application's requirements are not satisfied. And then, of course, you do have the distributed applications, such as distributed databases, where you have the processes running on multiple hosts, and data is distributed across multiple servers. So you have a sort of a multi-point to multi-point kind of scenario where you need coordination. I will only talk about the point-to-point in this talk. Okay. So what are some of the features in going end-to-end that are relevant from a QoS perspective? So one of the most important ones, of course, is the storage access protocol. And right now, the NVMe protocol is becoming the de facto standard because it's much lower latency, it's hardware supported, far lower latency, for example, those traditional protocols like SAS and SATA. And the protocol latencies could be 5 to 15 microseconds. So we'll be talking about mostly NVMe. NVMe does provide a fairly elaborate QoS arrangement. There's a picture here, for example. It supports priority queuing. It also supports weighted round robin. So if you can make use of those QoS features, if you can provide the right hints and use those features, then at least at the protocol level, you will be able to provide the desired QoS. There is actually, NVMe is actually a local access protocol, and there is a network extension to it called NVMe over Fabric. And it's a pretty simple extension. I don't want to go into the detail. Essentially what it does, it prepares what is known as a capsule and sends the command capsule over the network to the other side, to the controller side, and then the controller works on it, and then it sends the response back. Okay, so NVMe is one. There's another feature that recently has been added to the NVMe protocol, which is called the Determinism Control. And basically, the idea is as follows. The idea is that so a normal SSD does its background activities whenever it pleases. What if we confine those background activities to certain periods, and those are known as non-deterministic periods, NDT. And then there are deterministic periods where it doesn't do any background activity. So the idea is that if you have a high QoS, then you can make all of those requests during the DT period, whereas those that don't require the QoS, those requests could be made during the non-deterministic period. Obviously, that immediately raises the question. Let me see here. Okay. I think I have a slide missing, but nevertheless, I can explain to you. So, so basically, you would need two copies here, because any given SSD could be in either one of these two modes. And therefore, obviously, you cannot say that you're not going to make a high QoS request when the SSD is in the non-deterministic mode. So you would need two copies of your data, and you want to arrange it in such a way that at least one of those two copies is in the deterministic mode, and then you can provide this kind of a service. Okay, so that's one. Okay, now coming to the network. So I will talk about some of the QoS features that we need to implement using the standard networking technology. But in addition, there has been a lot of work in terms of coming up with these so-called smart NICs. And the smart NICs traditionally were the ones where they're just doing a simple protocol offload, and now the smart NICs do all sorts of additional stuff, and I'll talk about it later. And there are many companies involved in this. Intel has something called ADQ, and it can do QoS-based queuing and transmission. NVIDIA has another product, and Sando has another product, and so on. Okay, so let's talk about the network QoS. Now, obviously, for a longest time, we had this IP QoS, DSCP. The problem is that it's not very useful. The reason is that it's all based upon the loss and upon the packet loss, which is totally undesirable in a data center environment, and it is done hop to hop. What you need is a kind of an end-to-end QoS control. Now, to handle the problem of not having the loss, there are some TCP proposals known as data center TCP proposals. In particular, there is something called just DC TCP, data center TCP. It does avoid the packet loss, but doesn't provide the QoS. And the way it works is that it uses the explicit congestion notification, ECN. And based upon what fraction of the packets come marked with the congestion notification, it tries to do a window flow control. Okay? So I guess the details are not terribly important. Basically, what it does is that there is this fraction of packets that are being marked as having seen the congestion. You smooth it out using exponential smoothing, and then use it in the TCP window flow control. And here's a more detailed picture as to how this works. In the regular TCP, when you dump the packet, there will be a timeout, and then you do the retransmission. In the data center TCP, if your buffer at the switch is getting full, you mark the packet with the ECN bit, and when the packet gets to the other end, you send a ECN echo, and then as a result, you can do a window modulation. Okay. So TCP, of course, is a very popular protocol, and we would like to use that as much as possible. However, with these very high-speed technologies, it's necessary to use protocols which are much lower latency than TCP. And of course, the most popular of them is the remote DMA or RDMA. RDMA, of course, comes, it's not a Ethernet native, it comes from InfiniBand. It's a user space protocol, avoids a lot of the overhead going through the kernel, but it has been implemented with hardware support on Ethernet. The current implementation is known as RoCE, RDMA over Converged Ethernet. It's becoming very popular, and it runs on top of UDP. So there is some congestion handling in RoCE. It uses some data center Ethernet features in terms of the priority flow control and QoS classes. But data center Ethernet is a layer 2 feature. It's not really a higher layer feature. And the other problem is that since RDMA runs on UDP, there are no X. So for example, ECN-like mechanism will not work directly in this case. So there is another protocol known as DCQCN. And this is kind of like a DCTCP implemented in the RDMA context. So that's the easiest way to think about it. So it uses the ECN feedback. And since you don't have the acknowledgement packets, it actually sends an explicit packet known as a congestion notification packet every n microseconds. And once you have the congestion notification sent to the sender, then the sender can use it in essentially the same way that DCTCP uses it for congestion control. This also does not support any QoS. Okay. So obviously the problem is that with both of these protocols, if you had, for example, 10 gigabit bandwidth, and you had 3 applications with different QoS requirements, they will get equal bandwidth. They will get 3.33 gigabits per second, whereas your target might be to divide up the bandwidth in the ratio 1:2:3, something like this, but that wouldn't be possible. I keep track of the time here. You're doing good. All right. So we have been working on a protocol that we call Qos Aware Tcp. And we have done a lot of work on it. We're implementing it in the kernel and the Linux kernel right now using ECN capable switches. So I'll show you some results on that. So what is the idea? The idea really is that with QTCP, we define a target. So there is either a target throughput or a target delay. And then we define a quality factor based upon the target throughput and the estimated throughput that you're achieving, or the target delay and the estimated delay. So the quality factor is the ratio of these two things, the target and the estimator. And you can see that the ratios are reversed in the two cases. So in both cases, our goal is to make the quality factor less than equal to 1. And if you can do that for every flow, then you will be able to satisfy the QoS constraints for every flow. Okay. So we basically took, so without going into too much of detail, so basically we took the DCTCP congestion control and we modify it to take into account the quality factor. So you can see here these three branches of this window modulation. And the middle one is exactly what DCTCP uses. The top one is your usual window increase when there is no congestion. So nothing interesting about that. The interesting part is the bottom part where the window modulation is proportional to the quality factor. And this is the part that does the trick and provides us with the QoS that we desire. So let me just show you some results here. So we have a 10 gigabit link, but we are trying to push through 18 gigabits per second. Obviously, we cannot. So the idea is that in this kind of a congestion situation, we want to divide up the available bandwidth of 10 gigabits per second in the ratio of 1 to 2 to 3. So on the left-hand side, you have the result for the QTCP. On the right-hand side, you have the DCTCP. DCTCP, as expected, divides up everything equally among all the flows, whereas the QTCP does a pretty good job. It comes pretty close to what the desired ratios are. Okay. We actually carried out and we did a lot of work with this other protocol as well, the RDMA protocol, DCQCN. We again implemented that as well in addition to QTCP. And again, I'll show you, this was a lot of work, of course. You see the results, which are very similar to what you see for the QTCP. We're calling this as QRDMA. So again, the bandwidth gets properly divided, whereas in the regular DCQCN, everything is divided equally. And also, here it shows a behavior with respect to what happens when you have a whole bunch of flows directed at a single link. That's the in-cast degree. And we do well in terms of in-cast degree as well. You can see that different classes get different throughput regardless of the in-cast degree. We went even a step further, and let me explain to you why we did that, which is the mixture of QTCP and RDMA. So the motivation for this is, as I already said, that the storage is always remote. Now we have these emerging persistent memory technologies, which are very fast, but they are very expensive. So what people are trying to do is they are talking about having a remote persistent memory. So you have gobs of memory located in one server, and then different hosts can share it. So again, you are going over the network. And now, since this is a memory model, you better provide a really, really good latency. Otherwise, it's not going to be very useful. So there is a reason to mix the QTCP and QRDMA, but you want to make sure that you get very low latency through the network for the for the RDMA packets or for the memory packets. So what we do is that in addition to end-to-end, we also implement the QoS treatment in the switches themselves. And by doing that, we are able to achieve this objective. So here is again some results, and this only shows the throughput, not the latency, but kind of gives you an idea of what's going on. So basically the idea is that, now here this is a sort of an extreme case. It shouldn't be like this. The point is that you don't want to burden the memory traffic. So memory traffic should be able to grab whatever bandwidth it wants to grab, and then all the storage traffic suffers. And this is what is being shown here, that with this mixed treatment, you are able to let the RDMA traffic grab whatever it wants to grab, and the rest of it is divided up according to the QoS objectives for the remaining bandwidth. Now, the reason I said this is extreme is you definitely don't want to grab a whole lot of bandwidth for this kind of a purpose. But here, just want to show you that even in extreme case, it works pretty well. Okay. So that's about the networking part of the QoS. Now let's get to the predictable latency mode. And since I guess I'm running a little bit short on time, I will abbreviate this part of it so I can get to some interesting stuff which is yet to be looked at. So as I mentioned earlier that we have this NVMe 1.4 feature where you have this deterministic window where the SSD doesn't do its background activity, and the non-deterministic period where it does. And this feature is available at the level of NVMe set. And there's quite a complex structure in the NVMe. I don't want to go through it. You have this notion of NVMe system, endurance group, NVMe set, and so on. And this feature is available at the level of NVMe set. I think that's enough. Okay, this is a slide I was looking for earlier. All right, so the point is that if you're going to use this mechanism, then you need multiple copies, at least 2 copies. And the green is when that particular copy is in the deterministic mode. Red is when it is in the non-deterministic mode. And as long as you have multiple copies, and as long as you have at least 2 copies, which are not simultaneously in the non-deterministic mode, you would be able to direct all your high priority requests to the non-deterministic mode. Okay, so that's sort of the idea. So what is the problem? The problem is that it's not very well defined as yet. First of all, it doesn't tackle the case of what happens when there are multiple hosts trying to compete and trying to share storage, like what will happen in a database scenario. The second thing is that, yes, it talks about right handling, but it doesn't do a very good job. So what is the issue with the right handling? Actually, I can talk here. The issue is that when you're in deterministic mode, you don't want to do any writes, actually. You want to hold off all the writes, put them in a buffer, because the writes might trigger some background activity. So you want to put them in a buffer and then do all those writes during the non-deterministic period. But then the question is how big the buffer is, what happens if the buffer overflows, and there are all kinds of issues like that. So we tried to tackle this problem in 2 ways. One is that we tried to tackle the multi-host issue by putting a coordinator in between, and all the hosts talk to this coordinator, but the coordinator looks like just like another host to the device. So the device doesn't know any better. So the coordinator pretends to be a host, goes and grabs the information. There's a publish subscribe interface here between the device and the host, goes and grabs all the information, and then it gets the request from the host for the allocations. It does the allocation, and then all of the data transfer is done out of band. So the data transfer doesn't go through the coordinator. The coordinator basically tells, okay, you host number one is going to get 20 IOs in a current period. You host, you're going to get 40 IOs and so on. So it just does the allocation, and rest of it happens outside. So there's no bottleneck involved here. It's just a coordinator. So we designed that. And by doing that, we are able to provide this QoS differentiation. As you can see, that the high QoS gets a very low latency, then the medium latency, and the high latency. Okay, I will not talk about this figure on the right. A little bit out of time. So now we ask a interesting question here. So actually, unfortunately, this deterministic, non-deterministic feature, unfortunately, is still not available in commercial SSDs. And then there is a whole installed base of SSDs out there. So what are we going to do about that? Obviously, we're not going to rip them out and replace them with these new fancy SSDs whenever they come out. So we decide to design a solution where we can use just the regular SSDs, and we call it PLM Lite, predictable latency mode Lite. So what we do is that we still have this coordinator, and we handle both reads and writes. So we need a write handling agent within the controller. So we designed that. But what we are going to do is we are going to make use of some of these emerging technologies, such as to try to achieve some level of determinism. So that becomes our buffer. So what happens is that we still pretend that we have these deterministic periods and non-deterministic periods, even though the SSD by itself doesn't. And then during the non-deterministic period, we handle all the SSD writes. During the deterministic period, we put everything in the Optane buffer so that it doesn't trigger any garbage collection in the SSD. And then we push them out to the SSD during the non-deterministic mode. So we get some decent results by doing that. But as you can see very clearly that they are not quite as good as we would like. So here is the baseline, for example, that is without any persistent, without any use of this DT and DT business. And then if we use this DT and DT business with a regular SSD along with the Optane SSD, we are able to give much better and much more deterministic latency to the high QoS class, as you can see here, which is the blue line here. But the medium and low classes suffer. And you see the same behavior here. This is 30-70 read and write, 70-30 read and write. That again, you get a very good behavior for the high QoS, but you get worse behavior for the low QoS, which may not be so bad, because after all, if you're trying to get a deterministic latency for some selected applications, you're able to get that. Others perhaps have to suffer a little bit, but maybe it doesn't matter. And these are the read latency, and the write latency is uniformly low. This is for the baseline case, the red curve, and this is for ours. It's uniformly low because obviously all the writes are initially going to the Optane, and therefore you achieve a very low write latency. So that's not a problem. Okay, so I have one last slide left. I think I'm doing well in terms of time. So there are a lot of interesting things happening, actually. And that's what I want to leave you with. So I had mentioned this smart NIC, and they're becoming very popular. Now, the companies are going way beyond the traditional notion of smart NICs. And there are all kinds of acronyms floating around that you will see. DPU, Data Processing Unit, this is NVIDIA's term. IPU, Infrastructure Processing Unit, that's Intel's term. DSC, this is another company, actually, I can't pronounce the name. So all of these companies are coming up with these much more expanded functionality in the NIC itself, so that the NIC is not just accelerating your TCP, for example, the way it used to. It's doing a lot more. And in fact, VMware has a project called Monterey, for example, just to give you an idea as to where this whole thing is going. So what this project is doing is that it's using this smart NIC technology to virtualize a lot of the functions right there. So for example, you can virtualize your NICs, you can virtualize a lot of storage functions and other types of functions, and then you can assign those virtualized functions to either the local machine or even the host machine over the network. So you can imagine, for example, that there is a bunch of GPUs sitting here on the platform, and there are no GPUs on other platforms. So this NIC can virtualize these GPUs and distribute these GPUs, virtual GPUs, to a bunch of hosts which don't have their own GPU. Similarly, it can do a lot of other functions, such as these multiple levels of storage, virtualization, and so on. So this is a very exciting technology, actually. And there's a lot happening in this space. Obviously, the machine learning comes in a big way here. Again, you want to do a lot of machine learning here. So what VMware is trying to do is they will run their entire virtual machine in the NIC itself, and then provide a lot of functionality through the NIC, what used to be in the CPU. So the CPU is no longer dealing with these infrastructure functions, whether they are storage or networking. CPU does its heavy duty processing. So the question is that once you have a scenario like this, that you have a lot of these virtual functions allocated not only to the local machine, but to the other machines as well, how do you do QoS in this kind of environment, particularly when you have these heavy duty applications, strict tail latency requirements, and then you have these storage devices, for example, which can easily saturate the network, and other functions, security functions, for example, which place further stress on the network and the CPU of the network, CPU of the NICs, for example. So that's a problem to be tackled in the future. I don't have anything at this point, but we would like to look into this and invite you to look into this space. It's a very interesting and exciting space to look into. And that's the end of my talk. And I'm ready to take questions.